All right, thank you for the invitation. Thanks for having me. So this is, I think, the first talk I've given in almost 2 years, not on the black hole information paradox. So I'm looking forward to it. This is, cosmic censorship is something that I've been interested in and working on for some time now. As you can see, this is based on 2 papers, one with Gary Horowitz, who is my former advisor, and one with Osmund Folkestad, who is my current student. So there's a bit of a generational aspect to this work, which, we're continuing the work that has been started before. All right, so without further ado, let me begin with a little bit of motivation. So why cosmic censorship? And I'm not, even though this is Berkeley, I'm not going to assume that everyone necessarily knows what cosmic censorship is. So let me say a few words about that. So just to begin with geodesic incompleteness. So that's the statement that generic initial data evolves to form singularities in GR. This is something that we know is true for an adequate definition of the word generic. And this is just a phenomenon in general relativity that comes about from the equations of motion and various nonlinearities in there. Now, this was pretty nice in the sense of those of us who work on quantum gravity might have hoped that if generic initial data evolves into singularities, and singularities in general mean strong curvature, then maybe we would be able to observe strong quantum gravity effects from large singularities that live outside of event horizons. This might have been really good for us as quantum gravity practitioners. Now, there's life is never quite that easy. Generically what happens is that, yes, singularities do form from the evolution of generic initial data, but as far as we can tell, singularities like to live behind event horizons when they form from the collapse of matter. And the hypothesis that this is in fact always the case or generically the case is in very rough terms, the so-called weak cosmic censorship conjecture. Now, this is also partly motivated by the fact that to our knowledge, we have not observed any naked singularities, the formation of matter collapsing to form a naked singularity to date. It's in principle possible we've seen something, didn't know how to interpret it, but as far as we know, this is not something that we have observed. So this hypothesis that singularities generally live behind event horizons is in keeping with what we've seen so far in the universe. So a few words about the status of cosmic censorship. There are actually well-known counterexamples, the so-called Gregory-Laflamme type instabilities, the black ring, the black string, Myers-Perry black hole. So there are known counterexamples in 5 dimensions and higher, and these have existed for a long time. And now you might ask, given that we know that there are counterexamples, why are we still looking into cosmic censorship as something that might be true? And well, there is a sort of vague and somewhat ill-quantified sense in which these pinch-off singularities are small. And so maybe they're not such bad violations of weak cosmic censorship. And there's also the fact that they don't exist, as far as we can tell, in 4 dimensions. So maybe 4 dimensions is somehow special. And even if it's not, these pinch-off singularities, well, they're really small. They're, as people like to say, they're violations of the letter of cosmic censorship, but perhaps not the spirit of cosmic censorship. However, recently, there was a discovery of a class of fairly generic naked singularities in AdS. And when I say generic, I mean that these correspond to an open set in the space of solutions to the Einstein equation. So this is the sense in which we use generic for cosmic censorship. So this is I would say, a gross violation of cosmic censorship. This is in 4 dimensions in AdS. Admittedly, not in asymptotically flat space. This is for asymptotically AdS. There was also I would say, somewhat conclusive counterexamples that was found recently in 4-dimensional asymptotically flat space. I say semi-conclusive because it was done numerically, and even though the numerics looked like they might converge to something that gives a violation, it would require a very long amount of time to simulate, and they did not have the resources to do that. So it was a little bit, it was only somewhat conclusive.
Netta?
Yeah.
Are you going to say more about these generic naked singularities by Horowitz and others?
Yes, I will.
I thought there were some reasons to have some reservations about those examples as well?
So it depends on which examples. I would say the hovering black holes, seeing that they found seemed pretty robust. In cases when they started to include other dilaton fields and so on, you might have been a little bit more concerned.
I thought the concern had something to, I may misremember this, it's been a while since I looked at it, but I thought it had something to do with with whether this is actually a dynamical evolution and it's something that happens in finite time, or whether you're just dialing some parameter.
Yes, so I think this depends on which of the papers you're referring to. For some cases, they were just dialing up a parameter. So indeed, you are right about that. I think that, so in one paper, I believe it was Crisford and Santos, I think they actually did do a dynamical evolution. Of course, once they couldn't conclusively say that, the Kretschmann scalar literally blew up because it's numerics, but they found pretty good evidence to suggest that it does in a region that that probably communicates with the asymptotic boundary. So you could say none of these are analytic solutions where we can actually find what region is in causal communication, where the event horizon exactly is, and ascertain for a fact that there's that the curvature actually blows up there. But so all of these, you could say, are really indications that most likely cosmic censorship is violated. I'll say a little bit more about the details in a few minutes, but you're right to say that there's a sense in which these are not open and shut violations. So the question that we could be asking, maybe we should be asking for the question rather than an assertion, is the weak cosmic censorship conjecture actually false? If it is false, then maybe we should ask where should we be looking for naked singularities in our universe? Would be really exciting to see one if we knew where to point our telescope. So of course, maybe it's not false, as Raphael said. Potentially these are not real counterexamples. So that's something else to keep in mind.
Netta,
yeah.
is there a sharp statement that one could make, like a revision of weak cosmic censorship given all of these apparent counterexamples? Is there some clean statement that one can make?
So I will argue yes. I guess I'm being you're both these last two questions sort of preempting the rest of the talk. So maybe I will get to that shortly. I would say that what I'm going to do in this talk is I'm going to talk about how to derive aspects of cosmic censorship, consequences of cosmic censorship from AdS CFT. And in my opinion, one of those consequences, which is in particular that trapped surfaces don't lie outside of event horizons, you could, if you wanted to, take that to be the statement of cosmic censorship. And say, and in that sense, that circumvents these Gregory Laflamme type instabilities that I believe do not have trapped surfaces outside of horizons. And I don't know at this point, this is work in progress, whether these singularities that were found by Gary, George, and others actually have trapped surfaces outside of horizons. I don't know yet. This is work in progress. But even if they do, then I would say they violate cosmic censorship. But maybe that's a statement more about these not being good solutions of GR and not having a good UV completion. So I'm maybe let me postpone any further questions on that because I'm going to spend a little bit of time talking about it in a few minutes. And in a few minutes, I really mean on the next slide. So these recently discovered violations of the cosmic censorship conjecture, the weak cosmic censorship conjecture, also happen to violate the weak gravity conjecture. At least most of them do. And that's suggestive. It could be a red herring, or it could also be an indication that weak cosmic censorship could be false in classical GR, but could be true in valid semiclassical limits of quantum gravity, maybe cosmic censorship or some appropriate reformulation of it, something along the lines of trapped surfaces don't lie outside of event horizons, could be thought of as some kind of a swampland condition. And that sounds all very, that sounds nice, but how do we test this hypothesis? And my answer to questions like how do we test things in quantum gravity is usually, well, let's use AdS CFT. So in this talk, I'm going to use AdS CFT to test various aspects of cosmic censorship and try to prove aspects of cosmic censorship from basic tenets of AdS CFT. So I'll spend the first part of this talk just explaining the various terminology that I'll be using, trap surfaces and horizons and so on. And then I'm going to talk about two consequences of cosmic censorship, two things you can prove from cosmic censorship that you can also prove independently of cosmic censorship from AdS CFT. And so, which suggests that some version of cosmic censorship can probably be proven in AdS CFT and may be valid in quantum gravity, at least in the classical limit of quantum gravity. Everything I'm going to say now, except for maybe a few words in the summary, is going to be purely classical. So in AdS CFT, I'll be taking the large N limit. All right, so let me begin with maybe a slightly more rigorous explanation or definition of what we mean by cosmic censorship. So Roger Penrose formulated a somewhat vague version in '69, where he just essentially said naked singularities are invisible to an asymptotic observer, other than an initial Big Bang singularity. The more precise version by Garish and Horwitz from '79 is that the maximal Cauchy evolution of a set of generic asymptotically flat, or you can also generalize this to AdS. Initial data is asymptotically flat, or appropriately asymptotically AdS, and strongly asymptotically predictable. In particular, it's going to have a complete Scri plus, or in AdS, a complete conformal boundary. So this is a definition that we would ordinarily, that's what we would mean by cosmic censorship at this point, even though in '69, there was sort of a slightly different way of thinking about it. So let me say just a few more words now about these violations of cosmic censorship in a bit more detail. So in 5 or more dimensions, we have these instabilities, these pinch-off instabilities. So you have this beautiful images by numerical relativists who have simulated the black string, also black ring and Myers-Perry black hole, to find that these result in the sort of pinch-off singularities that the black string ends up pinching off. And at the moment of pinch-off, you have a so-called naked singularity. And more recently, these counterexamples for asymptotically AdS for initial data. And also there is this somewhat questionable counterexample for asymptotically flat in 4 dimensions. So again, the initial known violations were very mild. This pinch-off singularity, it's critical collapse. Critical collapse is usually is not generic, sort of very fine-tuned initial data. And the pinch-off singularity is very small. You might imagine that, well, these are tiny regions, most likely very difficult to resolve in quantum gravity without any effects being easily visible to asymptotic observers. So maybe you might imagine you need a huge amount of computational power to figure out that some radiation came from these Planck-sized regions in these mild violations, these Gregory-Laflamme type violations. So this suggests, or potentially might suggest, that a relaxed version of cosmic censorship is still valid if you can find a good way to exclude these pinch-off singularities. You can sort of quantify in what sense these are small, so you can allow them in your relaxed version of cosmic censorship. These recent counterexamples are a little bit more difficult. So this, what they found is that the curvature appears to grow without bound in an extended region. And again, this is numerical. So as Raphael pointed out, maybe you shouldn't trust it 100%. Maybe it is, maybe the curvature is actually bounded. But potentially not. They do seem, at least some of them seem fairly robust to me. So you could worry, as I said before, that cosmic censorship might just be altogether a false statement because we haven't understood various aspects of GR well enough. As I said before, this might be very good from the perspective of observational evidence for quantum gravity, but it will be very problematic. There are many foundational results in GR that assume cosmic censorship. For example, the Hawking area theorem, which we know and love and would prefer not to give up on. So that's something that definitely assumes a cosmic censorship, or well, it assumes a version of it. So these counterexamples, Christopher, Horowitz, and Santos found, and also Wei, these are for Einstein-Maxwell in AdS4. And what they found is if you add a charge scalar and the charge to mass ratio satisfies a conjecture about quantum gravity, so-called weak gravity conjecture, then cosmic censorship is no longer violated. There were slightly more questionable examples in dilaton gravity, so where the weak gravity connection is a little bit more tenuous. But this sort of brings up an idea that even though cosmic censorship can be badly violated in solutions to GR, it won't be violated, except potentially by these Gregory-Laflamme type instabilities in solutions to GR that do admit a UV completion. So the logic in this talk is to see if we can derive statements like cosmic censorship from our known quantum theory of gravity, the AdS CFT correspondence. Which leads me to the Penrose inequality. Oh no, sorry, which leads me to trapped surfaces and horizons. I'm one ahead. So first we kind of have to quantify what do we really mean by very mild violations of weak cosmic censorship? How do we want to permit, to allow something like that? Now, again, intuitively speaking, we might mean that there are extended regions of high curvature, and these are always going to be hidden behind event horizons. Basically, what we want is that classical results like Hawking's area theorem should be true. And one condition that's necessary for this is that trapped surfaces always lie behind event horizons. So just let me define what trapped surfaces are referring to here. So here we have a compact codimension 2 surface, sigma, and it has the ingoing null rays fired to the feature, which I'll call the L direction, and the outgoing ones, the K direction. And by outgoing, I mean if you have an asymptotic boundary, and these are directed towards the asymptotic boundary. So a trapped surface is defined as a codimension, it's a compact codimension 2 surface that has the expansion in the outgoing direction is negative, and the expansion in the ingoing direction is also negative. So intuitively speaking, that means that the light rays are contracting as you evolve inwards towards the interior of the surface, which makes sense. That's kind of what we see in our day-to-day life. If we imagine what happens to light rays as you go inwards, well, they converge. But for a trapped surface, the outgoing ones are also converging. So the cross-sectional area of the surface generated by these K congruents, by these K light rays, is going to have area that's decreasing as you evolve away from the surface. So intuitively, you would expect that something like that, where both light rays are decreasing in cross-sectional area, signals very high space-time curvature. More concretely, the singularity theorems guarantee for us, under assumptions such as the null energy condition, that there is a singularity in the not too distant future of a trapped surface. So that intuition is in some sense well-founded. Now, if trapped surfaces were to always lie behind event horizons, then that means that singularities that are predicted by the singularity theorems should also lie behind event horizons. So here I've drawn a trapped surface, and the light rays from this trapped surface are going to the singularity. In particular, none of the light rays from this makes it out to the asymptotic boundary. So cosmic censorship is, in the formulation that I gave as Horowitz and Garish did, predicts that trapped surfaces will always lie behind event horizons. So this is a proof that you can find in Hawking and Ellis or in Wald. Now, a violation of the statements is essentially a violation of global hyperbolicity, or more generally, a violation of strong asymptotic predictability, which is something that follows for cosmic censorship. So a very useful surface to use as the characterization here, the so-called apparent horizon. So here I've drawn a Cauchy slice of a spacetime with, here I've drawn an event horizon. Maybe we don't want to assume cosmic censorship. We don't want to assume the event horizon lies outside of the apparent horizon, but for intuition, I've drawn it that way. So an apparent horizon is the outermost surface on a Cauchy slice, where the expansion in the outgoing expansion is 0 and the ingoing expansion is negative. It's often defined as the boundary of the set of trapped surfaces on a particular choice of Cauchy slice. So there's a sense in which you can think of any statement that you want to be true about trapped surfaces should be marginally true about apparent horizons. For example, if you want your trapped surfaces to always lie behind event horizons, then you don't want apparent horizons to lie outside of event horizons. As an example of apparent horizons for stationary black holes, the event horizon can be foliated into surfaces that are apparent horizons. Now, if it weren't true that apparent horizons do not lie outside of an event horizon, then the Hawking area law would be false. So the area law is essentially an application of focusing, that this derivative is always non-positive. And you basically end up having to show that the expansion on the horizon is non-negative, which could not be true if there were surfaces on the event horizon that were trapped. If surfaces on the event horizon had negative theta. So this is just an illustration of the fact that there are consequences in GR which we think are results in GR that we think are very fundamental and require at least some version of cosmic censorship to be true. And this leads me to the so-called Penrose Inequality, which is a consequence of cosmic censorship. It can be derived from cosmic censorship and a couple of other assumptions. And it is a statement about the behavior of the apparent horizon, of apparent horizons in general. So here's how Penrose's original idea went. So suppose we have some four-dimensional asymptotically flat spacetime with total mass m and apparent horizon sigma. Cosmic censorship tells us that apparent horizons lie behind event horizons, okay? And let's make the assumption, which is a little bit flawed, and I'll say more about that later. But for now, let's assume that the area of an apparent horizon is smaller than the area of the event horizon on some Cauchy slice. Now this is a flawed assumption. It's known to be false in certain cases for the definition of apparent horizon that I gave. I'll say more about this in a little bit. Now, let's assume that's true nonetheless. Now we know by the Hawking area theorem that the area of the event horizon only increases with time. And here we are assuming that apparent horizons lie behind event horizons. In other words, we're assuming cosmic censorship. Then that tells us that the area of the apparent horizon, by this bullet point, is smaller than or equal to the area of the event horizon at some finite time, which by the Hawking area theorem is less than or equal to the area of the event horizon at some late time. And now if you also assume that any black hole settles down to Kerr, or Kerr-Newman, then you say, oh, well, the area of the event horizon at final times, being very late asymptotically, will be approximately equal to the area of Kerr with mass m, which is going to be less than the area of Schwarzschild with mass m, which in 4 dimensions is just 16 pi m squared. And so altogether, you find that the area of the event of the apparent horizon is going to be smaller than or equal to the area of the Schwarzschild with mass m in 4 dimensions. Or put differently, you find this inequality for the area of an apparent horizon. And so you could say, well, okay, now cosmic censorship implies this very quantitative statement. So can we test this quantitative statement? Can we see if this statement is true in general? Now, just to say, if you're worried about the fact that this is asymptotically flat or 4 dimensions, you can do this exact same derivation in higher dimensions, or in particular for AdS, which will be interesting for us in this talk. And in the general AdS Penrose inequality is that if this is an apparent horizon in d dimensions, then the area of sigma is going to be less than or equal to the area of a static AdS black hole with mass m. So that would be the Penrose inequality in AdS. Now, this argument has some issues. For example, the area, assuming that the area of the event horizon is smaller than the area, that the area of the apparent horizon is smaller than the area of the event horizon. It assumes that all black holes settle down to Kerr. But if you sort of ignore those flaws for just a moment, or those caveats for a moment, then it suggests that the Penrose inequality derives from cosmic censorship. Now, in reverse, if Penrose inequality is true, it's good evidence in favor of some version of cosmic censorship. Of course, the Penrose inequality is a much weaker statement than cosmic censorship. It doesn't imply cosmic censorship, but it seems like a pretty good litmus test. Now, proving cosmic censorship is very hard. We don't know how to do that. Maybe it's not really true in its current formulation. Perhaps we should try to prove the Penrose inequality directly. without assuming cosmic censorship. That might be easier. It's a quantitative statement. We could just try to just prove it and see if it's true in general. So what is the current status of proofs of the Penrose inequality? Well, proofs that don't assume the cosmic censorship proposal exist in four-dimensional asymptotically flat Riemannian case, meaning you work in a situation where you have a moment of time symmetry, where you have a static space-time. In situations like that, you can have a proof of the Penrose inequality. There's no general proof for the Lorentzian Penrose inequality in asymptotically flat space, and even less is known about the asymptotically AdS case. There's been some investigations, but really it's not very well understood. Now, we know that AdS is a good testing ground because it has these violations of cosmic censorship. So if we can prove the Penrose inequality for AdS, that would be very interesting because we know that there do exist these other violations. Now, we also might not expect that we can prove this inequality for general spacetimes, general solutions of the Einstein equation, given that we know that there are violations of cosmic censorship in AdS. But we might hope that asymptotically AdS spacetimes that have a CFT dual potentially do satisfy a Penrose inequality. And it turns out that they do. So this is a paper that Gary and I wrote in 2019. So let's take an apparent horizon. This asterisk here will be explained on the next slide. So let's take an apparent horizon with some other assumptions in an asymptotically AdS spacetime with mass m. And assuming the HRT proposal, holographic entanglement entropy, and assuming AdS CFT, we can prove that the area of sigma is less than or equal to the area of a static AdS black hole with mass m. So basically, the consistency of the holographic dictionary, and in particular the entanglement entropy entry, is enough, together with a couple of relatively mild assumptions, to guarantee that holographic spacetimes satisfy an AdS Penrose inequality. So how does the argument work? Well, we begin with the necessary ingredient in holography. Since we don't necessarily expect that this is true in general, it must be something special about holography that allows us to prove this. So the necessary ingredient is the HRT proposal. So we're working again just classically right now. So no quantum extremal surfaces at this stage. We're just talking about classical extremal surfaces. So the von Neumann entropy of a boundary region R, so rho R is the reduced density matrix on a boundary region R. This is computed by the area of an extremal surface that's homologous to R over 4GH bar. So this is a space-time diagram. This is just a moment of time slice. So, okay, we have this very, very valuable entry in the dictionary. How do we make use of it? Well, suppose we have some space-time with an apparent horizon. So sigma here is an apparent horizon in our space-time. T naught is where the boundary of its past hits the asymptotic boundary. We can construct a two-sided geometry which looks identical outside of sigma. And using this, we can prepare in this space-time it's an extremal surface, which is actually the HRT surface of this space-time, whose area is identical to the area of sigma. So this will actually show up again, so I'm going to spend just a couple of minutes talking about it. So the way this construction is done is that you take your apparent horizon and you fix the data in this region here, which is what Aaron and I call the outer wedge of the surface sigma. So this is everything between sigma and the asymptotic boundary. So this is the same in this spacetime and in this spacetime. These two are the same. Don't modify that. And then you prepare initial data for the rest of your spacetime by gluing in a stationary null hypersurface to sigma. And you have to satisfy certain conditions, and it turns out that you can actually show that there exists an extremal surface on this null congruence. And you can generate the rest of the spacetime by doing a CPT conjugation. So this here is the CPT conjugate of this surface over here. Now, the value of this is, or part of the value of this construction, is that the area of X and the area of sigma are identical because this is a stationary hypersurface. So the area of all of the slices is going to be the same. And it turns out that in order to actually do this construction, I need to define the asterisk that I was referring to as far as the apparent horizon goes. In particular, you need an additional condition on sigma in order for this to work. So this is what Aaron and I, perhaps somewhat unfortunately, called a Minimar surface. So a Minimar surface is very similar to an apparent horizon, but defined it's a little nicer. So it's a compact, marginally trapped surface, meaning theta k equals 0 and theta L is less than 0. It's homologous to a connected component of the asymptotic boundary. And the first requirement is that it's what's called strictly stably outermost. The intuitive version of what this means is that there exists a small deformation of the surface outwards that gives you a normal surface, a surface where theta k is positive and theta L is negative. So this is what mathematicians call strictly stably outermost. The second requirement is that sigma is the minimal area surface homologous to the boundary on a Cauchy slice of its exterior. So in other words, there exists some slice of this on which sigma is the minimal area surface. So this is what we call a Minimar surface. It turns out that under certain class of generic conditions, here is a slice of the exterior on which sigma is minimal. Now, under certain set of generic conditions, assuming things like smoothness, apparent horizons are Minimar surfaces. So I'm not going to distinguish between them. And whenever I say apparent horizon, you should just think that what I mean is a Minimar surface. And that's necessary for this construction. It's necessary for basically all of the proofs that I'll be talking about. So we're still in step 1 of the argument, but I promise we're making progress here. So if you assume the null energy condition, then it turns out that this surface X here is in fact the HRT surface of this spacetime. You can prove it. You can prove that this is the minimal area surface, extremal surface. So it computes the von Neumann entropy of the CFT state that's dual to that two-boundary geometry. So call that M prime G prime. And so what we know is that there exists a spacetime in which the area of the HRT surface is equal to the area of the apparent horizon. And therefore, there exists a state in the CFT that is equal to, whose von Neumann entropy is equal to the area of sigma over 4G H bar. Either that or the HRT prescription is missing something. So this is just an application of HRT to this space-time here, where we fix this and we've constructed a different interior to the surface sigma. Okay, so now we're on to step 2. So we have this new space-time. Now the important thing to note is that the asymptotic charges in this region here, the ADM mass, for example, these are identical in the original space-time and in this new space-time we constructed, because by definition, the new space-time has this region identical to the outer wedge of sigma. In other words, this region here is the same in this space-time and in this one. So that means that the asymptotic charges are going to be identical. Now, that immediately tells us that, so still over here. So that tells us that the mass, the ADM mass, is the same in both spacetimes. And that means that the CFT energy, which is by which we mean integrating the 0,0 component of a stress tensor, is going to be the same in both the old spacetime and the new spacetime. So so we can look at the microcanonical ensemble at this point. We say, well, we know the area of sigma over 4G H bar is the von Neumann entropy of some CFT state rho. And then we consider a maximization of the von Neumann entropy over all CFT states with the same energy, which of course gives us we consider with some small delta E gap, and that gives us the microcanonical ensemble. So this tells us that the area of sigma over 4G H bar is going to be smaller than or equal to the von Neumann entropy of the microcanonical ensemble. And it was recently argued, or I don't know if you want to call 2018 recently, but I guess I still would, that in the large N limit, the microcanonical ensemble is actually dominated by static black holes. So Don argued that the von Neumann entropy of the microcanonical ensemble is equal to the area of a static black hole with mass m over 4G H bar. So we can put all this together, And we say, well, the area of sigma is equal to the von Neumann entropy of some CFT state rho multiplied by GH bar, which is going to be less than or equal than to the von Neumann entropy of the microcanonical ensemble multiplied by GH bar, which by Don's paper is equal to the area of a static black hole with mass m. And so we find that the area of sigma of any apparent or any Minimar surface is bounded from above by the area of a static black hole with mass m. And in fact, you can repeat this argument for black holes with charge to get a charged Penrose inequality. So you'd be looking not at the microcanonical ensemble, but you'd have to also be including charge in that, but you can do that. So this gives us a proof of the Penrose inequality in AdS CFT using just the holographic dictionary. So the Penrose inequality uses a particular aspect of cosmic censorship that trapped surfaces don't lie outside of event horizons. And so if you think of how the Penrose inequality is derived from cosmic censorship, you could say, well, maybe the fact that we can prove the Penrose inequality in AdS CFT is good evidence that this nice aspect of cosmic censorship that gives us the Hawking area theorem, that trapped surfaces don't lie outside of event horizons, can also be proven in AdS CFT. Maybe that's true. And that, in fact, turns out with some caveats to indeed be true. So that leads me to recent work from this past December with my student Osman Folkestad. So the basic idea is the following. Again, an apparent horizon is the outermost boundary of the trapped region on a Cauchy slice. That's how it's normally defined. And we would like to prove that anything behind an apparent horizon also lies behind an event horizon. And so what we do is we're going to argue that Minimar surfaces always lie behind event horizons. And we'll do this by an important consistency condition on the HRT prescription. So once again, we're going to be using the holographic dictionary, in particular, the entanglement entropy entry. Now, we might argue that these lie behind event horizons, but as I'll show, that doesn't necessarily mean that trapped surfaces always lie behind event horizons. And I'll explain how that could happen. But what we can do, nonetheless, is to use the same coarse-grained space-time construction, this idea of fixing the outer wedge of an apparent horizon or Minimar surface and building this doubled space-time behind it. We can use that to actually prove that Minimar surfaces always lying behind event horizons implies that trapped surfaces also always lie behind event horizons. And this does take a certain set of assumptions to work. So I should say this part of the talk, the proof that trapped surfaces lie behind event horizons in AdS CFT, takes in more assumptions. It requires more assumptions than the Penrose inequality, which essentially just require the null energy condition and holographic entanglement entropy. So what's this consistency condition that we use that's so important for us? So the consistency condition is that the HRT surface has to be achronally separated to the boundary region whose entropy it computes. So here I have an extremal surface, the HRT surface of Scry. And let's suppose that it's actually not achronally separated from it, that it's possible to send a time-like signal from here over here. So we might imagine that we could turn on some unitary, and then it could propagate up to x and change the area of x. But if it could do that, then what would happen is that we could act on our state with the unitary and change the von Neumann entropy. Now, the von Neumann entropy is not modified by unitaries, so that should not be possible. And so an important consistency condition is that this surface X, the HRT surface, has to be achronally separated from Scry, or if it's the HRT surface of a particular boundary region, it should be achronally separated from that boundary region, from the domain of dependence of that boundary region. So in this coarse-grained space-time, so now we say, okay, we take some apparent horizon and we imagined we want to build this coarse-grained space-time. So how do we do that? Well, okay, the important thing is that we have to add in this null hypersurface goes between mu and x. And that in particular, that means that if there are no causal signals that go from x to scry, then there will be no causal signals that go from mu to scry. And so that means that our parent horizon, our Minimar surface, is future achronal to scry. Of course, it's possible that it could be past communicating with scry, but that's not a problem. We want a future marginally trapped surface to not be able to send future communications to the asymptotic boundary. And so from this, we show, and again, I'll go through the logic of this, under some assumptions that think that what's behind mu, both in the coarse-grained spacetime and in the original spacetime, is also going to be future achronal to scry. And then what we show is we use a very well-known math theorem, or somewhat well-known math theorem, to prove that if you have a trapped surface, generically, there will be a Minimar surface outside of it. And so that means that that's enough, proving that Minimar surfaces lie behind event horizons and that their inner wedges also lie behind event horizons is enough to show that trapped surfaces do as well. In other words, if for every trapped surface, for generic trapped surfaces, there is always a Minimar surface between them and the asymptotic boundary, then this is enough to show that the trapped surfaces always lie behind event horizons. Now, I said that there's there are more assumptions that go into this proof, and there's one in particular, which is, most of them are mild, but there's one in particular which in some sense is not mild. And so I should be honest and declare that assumption up front. We assume that what we call evaporating singularities don't form in classical general relativity. So what do we mean by evaporating singularities? Intuitively speaking, what we mean is singularities that don't just suddenly end. So some examples, I can give the precise definition. It's not that illuminating. It essentially means that you can't contain your trapped surface inside some nice compact set. So here are examples of singularities that are naked singularities, but they are not what we call evaporating singularities. So here is a time-like singularity, a naked time-like singularity, but it's not an evaporating singularity in the sense that it's sort of extended in all of these directions. Here's another this is a naked singularity, a time-like naked singularity. Again, this is extended for all time, or at least it might form at some point, but then it's extended for all time. So an example, here are two examples of what we call evaporating singularities. So there's this funny thing here, kind of a little twig of a singularity that would not be allowed. It's an evaporating singularity. We don't allow that in our proof. Or the original evaporating singularity of an actual evaporating black hole, we also do not consider that. Now, I will talk a little bit at the end about what that means for quantum corrections to this proof. Clearly, this is not an assumption that is justified in semi-classical gravity. It's not implausible that classical gravity doesn't allow singularities to just evaporate, but we know that we know that once you add quantum corrections, this can happen. So I emphasize this proof is classical, and presumably to generalize it to include quantum effects, we will need to work harder. But for now, just being able to prove that trapped surfaces don't lie outside of horizons classically, I would say that's already a big step forward. Okay, so this is an assumption we're going to make: no evaporating singularities in classical general relativity, or at least all of our results apply when evaporating singularities are not allowed. So under that assumption,
Netta?
Yeah.
Can you say in a little bit more detail what you mean by what the definition is technically for an evaporator? What does it mean for it to suddenly end?
Yes, I have a slide at the very end. Let me just scroll through everything quickly with the actual definition in it. There it is. Okay, so this is what the technical definition of the evaporating singularity is. I guess I could just leave it up here. Let me just say maybe in some sense. Okay, let me try to say a little bit more intuitively what this means. Essentially, we want a situation where if you can trap a singularity between two hypersurfaces, which are not themselves geodesically incomplete, in other words, they themselves are complete, they're not singular, then then yeah, so basically we want to forbid that situation. So we want to get rid of the possibility that you have these imprisoned incompleteness inside a compact set. So this here is the definition that we use, where I tilde plus or I tilde minus, that those refer to the CFT evolution. So in other words, I plus would just mean, well, I plus, but I plus tilde means as far as you can evolve the CFT. So if the CFT becomes sick at some point, even if the geometry of the asymptotic boundary continues to exist, that's where we stop. So we want for one, we want the event horizon to reach that point, and that's not 100% enough. We also invoke this assumption over here, which is this thing that allows us to forbid this imprisoned incompleteness inside between two hypersurfaces that are themselves complete.
Okay, thanks.
Okay. Other questions about this? Okay. All right. Okay, so under this assumption of no evaporating singularities, we show that if a Minimar surface lies behind an event horizon, no causal surface from it can ever reach Scry. Now, that might seem like it should be obvious that why do we need this assumption of no evaporating singularities to show this? I mean, this diagram clearly shows that X can't communicate with Scry, so clearly mu can't either. The problem is if this singularity just stops here and the asymptotic boundary continues, then you could imagine that a causal curve could get out this way and then eventually make it back out here. But if this singularity is not allowed to evaporate, then you can prove that that cannot happen. And so that means that literally there are no causal curves that go from mu to the asymptotic boundary if there are no causal curves that can go from X to the asymptotic boundary. And since consistency of HRT tells us that there are no causal curves from X to the asymptotic boundary, then we know, at least in classical GR, then we know that there are no causal curves from mu to the asymptotic boundary. Now what's left to show is that trapped surfaces lie behind Minimar surfaces. So far, all we've shown, like it's great, apparent horizons, Minimar surfaces, they lie behind event horizons. But that's not the results we're actually looking for. That's a result that's maybe enough to prove the Penrose inequality, but we want more. We want trapped surfaces to always lie behind event horizons. So we still have to show that. So for this, we use a very useful math theorem by Anderson and Metzger from 2008. So the theorem is as follows. So if you take a compact—
Sorry.
Yeah.
Before you get into the math theorem, I'm pretty sure you explained it and still I didn't get it. Why, in the example where, you know, your singularity suddenly ends, and so there's a causal curve from mu to some boundary that goes around the left side?
Yeah.
Why?
Not the left side.
What?
Sorry, please finish.
Yeah, so I was worried that then there's also a causal curve that goes from X to the boundary, and I'm confused why that would be acceptable.
Well, so you could imagine you have an evaporating singularity that sits right here, and somehow and maybe cuts off everything except for one curve that could kind of sneak through from mu.
Okay, got it. Thank you.
Yeah. Questions? Okay, so the math theorem that we use to prove that trapped surfaces always lie behind Minimar surfaces is the following statement. So if you take some compact space-like hypersurface, which has an inner boundary, this is the hypersurface sigma, and has an outer boundary, you assume that the inner boundary is trapped and that the outer boundary is outer untrapped. So theta k is positive for this over here, theta k is negative over here. Then you can show that this surface sigma contains a smooth, stable, marginally outer trapped surface little sigma. So this is giving us almost exactly what we want, in the sense that we say, oh, okay, if I have a Cauchy slice and my spacetime is asymptotically AdS, then I can always find so-called normal surfaces near the asymptotic boundary. And we're assuming our spacetime is asymptotically AdS. Now, I have some trapped surface in the interior, And then that immediately tells me that I have some marginally trapped surface in between the two. This is exactly what I want, except for the fact that everything here is about theta k and not about theta L. And for what we want, in fact, this also gives you the stability condition we need for Minimars, but the only thing it's missing is this negative theta L direction. Now you might, it intuitively seems clear that it should work in the sense that if you assume that this surface has theta L negative, and you pick this surface to have theta L negative, which you can always do, you would expect that probably you can, by suitably wiggling your Cauchy slice around, given that this surface exists on all of these Cauchy slices, that you'll be able to find one that's marginally trapped, that has theta L negative as well. And you have to actually make a mild additional assumption for this to be true. But you can actually prove it. This mild additional assumption has to do with what happens in the past of a trapped surface rather than in this future. And since in cosmic censorship, we're mostly worried about what happens in the future of trapped surfaces, this is not such a bad assumption to make. And so under this degenericity condition that you can prove that trapped surfaces generically will lie behind Minimar surfaces. And this doesn't require global hyperbolicity, so you can prove this in non-strongly asymptotically predictable spacetimes, which is important for us because we don't want to assume strong asymptotic predictability, since that's basically essentially the same as assuming cosmic censorship. So the upshot is the following statement. If there exists a trapped surface, again with this genericity condition, in a classical asymptotically AdS spacetime that satisfies the null energy condition, then one of the following holds. Either the spacetime has an event horizon and a trapped surface lies behind it, or classical general relativity admits solutions with evaporating singularities, or the spacetime has no holographic dual. So this is the upshot of what we proved. I would say it's a very good affirmation that most likely there is some version of cosmic censorship that holds an AdS CFT, even if that version is just the statement that trapped surfaces always lie behind event horizons. So let me, I think we'll have maybe just a few minutes left, so let me wrap up. So I want to compare and contrast the two results, because there's a sense in which you might ask, well, why did you bother telling us about the Penrose inequality when you could prove the stronger statement right away? You could prove the statement that trapped surfaces lie behind horizons, which implies the Penrose inequality. Well, the value of the proof of the Penrose inequality is that it's valid in the absence of assumptions about the type of singularities. So it's valid without assuming that there are no evaporating singularities. And I think that's pretty powerful, because I will admit that it's a strong assumption that there are no evaporating singularities in classical GR. I think it's true, but I can't prove it, and it's a strong assumption. We don't need it for the Penrose inequality. You can also get a not particularly interesting quantum generalization. It unfortunately, and I'll say that on the next slide, it doesn't coincide with the quantum Penrose inequality, the quantum generalization of this of the Penrose inequality that we get. But nonetheless, it's robust against quantum corrections. But of course, the downside of this is that the proof is not quite enough to conclude that trapped surfaces lie behind event horizons. It's a necessary condition for that, but it's not a sufficient condition. Now, the proof that trapped surfaces lie behind event horizons is it's a stronger result, but it also requires comparatively stronger assumptions. We need to assume something about the type of singularities involved. It also uses a math theorem, and it's not clear how we would go about generalizing that to include quantum corrections. That math theorem is very classical. I don't know how we would go from area to generalized entropy in that theorem. And nonetheless, though, the upshot is that it's a more fine-grained result in the sense of telling us what trapped surfaces are doing, as opposed to just this general statement that derives from no trapped surfaces behind event horizons. And it certainly is closer to a proof of cosmic censorship than the Penrose inequality. So this seems like good evidence for a version of cosmic censorship in quantum gravity. But what version would that be? I guess this circles back to Tom's question from earlier. So what version would that be is one of the things that obviously we need to think about next. Also, as I mentioned before, quantum corrections for the Penrose inequality. The quantum corrections for the holographic Penrose inequality don't give you what's the so-called quantum Penrose inequality. So how do we bridge that gap? In what sense are they telling us the same thing? Now, then there is the fact that once we include quantum corrections, we definitely know that evaporating singularities can occur. So what assumption is appropriate in semi-classical gravity that would allow all of the ingredients of the proof of trapped surfaces not lying behind event horizons to go through if we're willing to assume that there's some version of the math theorem that we can prove? In other words, the math theorem, being classical, is not the only hurdle here. There's also the fact that, well, evaporating singularities occur. We're going to have to find a way around that if we want to extend this proof to a statement that quantum trapped surfaces don't live outside of event horizons, or maybe they do live outside of event horizons. So, and which that leads us to the question, the million-dollar question: what is the correct formulation of holographic cosmic censorship? How do we prove something like that from the basic principles of AdS CFT? Is weak cosmic censorship, or some version of it, or the holographic version of it, a swampland condition? So I'm currently doing some work in progress with my student Osmond on violations of the Penrose Inequality in Einstein-Maxwell. I don't have any results to quote just yet, but it would be exciting if it's possible to violate the Penrose Inequality in Einstein-Maxwell and know that it has to be true nevertheless in AdS CFT. So then we would say, okay, well, that's a condition that has to be satisfied in any holographic theory. So with that, I think I'm probably running a little bit over. So thank you for your attention.
Let's thank Netta. So now we have some time for some questions. So anybody wants to start?
Are there any candidate conditions for what would replace this no evaporating singularities condition at the semi-classical level?
Well, I mean, as we have discussed in the past, some kind of a condition that says, oh, well, the singularity can evaporate, but in some sense not too badly. Something like that. I don't know. To be honest, I don't know how the proof would work, because it's pretty critical right now that once there's a singularity, there's sort of no way around it. And the causal structure is very different. So I will admit that I don't have any really good ideas, but I suspect that these sort of small, something like Hawking evaporation should be quantitatively different from that, a twiglet singularity that's sort of very extended and very, very violent. So it's sort of an instant of a naked singularity. I suspect that the power of the singularity sort of has to come in, but in what sense and how would fit into the proof? I don't have a good answer for that.
But I mean, what we were discussing, I thought was, what the statement of cosmic censorship would be. Mm-hmm. And I don't think you want anything like that, right? Because then you're just putting in the answer of cosmic censorship into the assumption.
Right, but I suspect my hypothesis is that cosmic censorship essentially boils down to the statement: no visible, no detectable quantum trapped surfaces unless you use maybe exponentially exponentially complex data in some sense that you can't detect them otherwise. And so if that's the statement, then that is a formulation of cosmic censorship. That sort of just gives you the answer though, so it's not particularly satisfying. But that's a sense in which it's related to what we were talking about in terms of what is the appropriate formulation of cosmic censorship and in what sense that's related to quantum trapped surfaces and where they are.
Hey, is it useful to consider in quantum case, in the future of mu, there is no kind of termination of the singularity or something like that?
So let me just go to a picture. So in a future of mu, there is no what singularity?
No, a termination of the singularity, evaporating singularity in quantum case.
Oh yeah, I mean, for sure. So if we have that situation, so there's a sense in which if my association of evaporating singularities in the quantum case are ones that don't make it to the asymptotic boundary, but sort of end, but do the end over here, that you can't sort of get around it. It sort of, in this picture, you would not be able to get around it in this way. You'd have to go in that direction, right? You'd have these singularities that don't make it all the way to the asymptotic boundary and just end somewhere in the bulk. There's singularities that live in the bulk and don't make it all the way to the asymptotic boundary. And so what I would like to see is a situation where that distinction is very important for the proof.
Yeah, I think you were probably answering, but I was saying what's wrong with replacing this lack of evaporating singularity with the lack of evaporating singularity, or kind of edge of the end of the singularity in the future of mu.
So you mean what's wrong with truncating the singularity here and allowing space-time out here? Is that the question?
Or evaporating singularity doesn't happen in the future of mu. It can happen somewhere
Oh,
else.
you mean, you're saying basically, what if it can happen somewhere but not in the future of mu?
Yeah.
So you would have to say this could work, but you would have to say it can't happen in the future of mu for any possible extension of the future of mu. So in the original space-time, you only have access, as far as the future of mu goes, you have access to this initial data. But to fix it, you also need to have access to initial data on this null hypersurface. And so you'd have to say in any space-time in which the outer wedge of mu exists, or in which this is the hypersurface you're fixed, it is not possible to add initial data here such that there is an evaporating singularity in there.
Understand, it's a strong assumption, but at least naive example with usual vanilla evaporating black hole, you can accommodate it, right?
That's right. Yeah, that's right. So you could weaken the assumption. Weaken the assumption of no evaporating singularities ever to no evaporating singularities in the future of apparent horizons. Yes.
Yeah, that's what I was saying. Yeah.
Maybe. So it's always nice to weaken the assumption. It's true.
Because certainly you have to, right? Because vanilla evaporating black hole violates that strong.
Yeah, I'm actually surprised by. I mean, I think what Yasunori just said seems like I must be missing something. It seems like the obvious solution to your problem, right?
Well,
that will still be true for an evaporating black hole.
Sorry, yeah. I can say only obvious thing. Yes.
Sure, but then you have to ask. I guess you have to ask, what is the evaporating black hole the only type of evaporating singularity that we could ever get?
Yeah, of course.
No, but that's the wrong thing to worry about. You have a much bigger worry, which is that something that we know basically for sure does happen doesn't satisfy your assumption.
Well, I mean, it only happens in semi-classical gravity.
Some weaker assumption is then satisfied.
Yes.
But the point is that this is a very simple trick to get around the problem that the key assumption you're making is already not satisfied at the semi-classical level.
Yes, this is true.
So that seems like it seems really great to me. I don't know.
Yeah, to me too.
Well, I mean, I should probably check the proofs and make sure that I'm not forgetting somewhere that we use this assumption more extensively. Off the top of my head, though, I think it works. We just weren't thinking very hard about the quantum case. We kind of wanted a classical result, but it shows that it pays to give talks about your work at various places.
Yeah.
I have a question. So you mentioned a few examples to cosmic censorship that exist. There's the Gregory-Laflamme instabilities, but you point out that those are really tiny, and so they kind of don't really count. Then there's the examples from Horowitz and friends where they found these counterexamples, but you can argue that in those examples you violate the weak gravity conjecture. So maybe if you insist upon having a UV completion. I was wondering, could you elaborate a little bit more on these semi-conclusive recent examples? Assuming that those are actually counterexamples, which category do they fall into?
When you said semi-conclusive, you mean the asymptotically flat four-dimensional case?
That's right.
So that one actually doesn't violate the weak gravity conjecture. That's Einstein's scalar, and again, they're pretty careful in the paper not to cast it as a definite violation. So I would not go ahead and say that's for sure. But it's also quite simple actually. But under the assumption that that actually does give a violation of cosmic censorship, there's no obvious connection to weak gravity there. Now, I don't know if you think that the weak gravity conjecture is literally the only Swampland criterion out there, then that might be a problem for that perspective. But if you are happy to say, okay, well, maybe there are spacetimes that satisfy the weak gravity conjecture, but don't have a UV completion, then that's a possibility there. Yeah, that's that one in particular does not have any problems with weak gravity.
Yeah. Okay. Yeah. I mean, that's what I was sort of hoping, is that maybe there's some other swampland sort of statement that is needed to exclude such possibilities.
Mm-hmm. Yeah, I also don't know if that they haven't been able to say conclusively if that spacetime has trapped surfaces outside of horizons. So they're just looking at large values of the Kretschmann scalar. So that's also another thing to think about, is that does that counterexample, if it's a legitimate counterexample, actually violate what I would say we could think of as an alternative formulation of cosmic censorship, trapped surfaces lying outside of horizons, or the Penrose inequality. Does it violate those? And that's a good question, but I just don't think they know currently with the numerical evolution that they've done.
Thanks.
Do we have any other questions for Netta? So if no, let's all thank Netta again. Thank you, Netta.
Hey, thanks.